just to, okay, just to say again, what we're doing here. So we have a code which is just doing this the same operation twice on the CPUs, right? So here we are using a GPU node, but of course we're not yet using any of the GPUs to do this operation, right? So just to come back to this picture here. So what we did was basically allocate the arrays in the CPU memory. Then we use the 20 cores to do the AX plus Y operation twice, right? And this GPU was basically idle on this GPU node that we were using so far. Okay? And this was done twice because, as I said, we will use the second part, right? So here where we say B, right? So this is done once up here, and then twice here the same way. So now this one we're going to use to write as a GPU kernel. So I just jump right. Okay. Good. So what are the steps to do this? So we'll take it a bit slow to begin with. Okay, so there's some things we need to do inside the main program, right? So inside main, some things we need to do outside of main. So, okay, some of these are trivial. So we need to add the Cuda runtime. It's just the header files of all the library functions we use. Then we have to add the kernel, okay, outside of this main program. And we need to add, okay, maybe you don't want to do this, you want to call Cuda memcopy directly, but we will be doing this. We will add something similar to this alloc function. Okay, what do we need to do inside main? And we'll go through this one by one, of course. Is we need to allocate the arrays on the GPU, copy X1 and Y1 to the GPU, call the GPU kernel, and then copy back from the GPU. Okay, that's just at a high level what we need to do. And so now I'll walk you through this, and I'll be doing it also in my editor here. So hopefully you will also be able to jump up and down and do it in yours. So the first thing, we add this include file in our main program. So somewhere here at the top, include and Cuda runtime.h. Okay. Okay. So now this is just the header file which has all the definitions of the Cuda functions that we will use. Okay, and then this is the interesting part. We add the GPU kernel, and for the moment, we will just add the GPU kernel the same way as we would do it on the CPU. So it's just a loop over all elements. And we will return to this later on to make it a bit faster. But for now, we just do it the naive way. Okay, so just copied that there and put it under where the CPU AX plus Y is called. So again, there's this global attribute that basically tells the NVIDIA compiler that this should be also compiled for the GPU. Okay, I'm doing a lot of things that I said I wouldn't do before, whereas I'm not looking at what thread idx.x is, thread idx.y is. So I'm not doing all that stuff for now. I'm just doing a simple loop over all the elements. Okay. And now, okay, you just have to copy this. Sorry about that, but it's basically just the function that allocates memory on the GPU. So this happens here. Okay. And then checks if this was successful, so that if it isn't, it just gives you an error, because if you don't check, then your code will just run through and will probably cause an error somewhere later in the program, and you won't know what happened. Whereas if you catch it here at the point where you actually allocate it, you catch it here, then you'll know exactly what went wrong. So that's why this function is useful. Okay. I will put it somewhere here underneath UL. Okay. So those were the 3 changes we did outside of the main function. Does anybody want me to, you need me to wait a bit, it's fine. It's better that we do some of it well rather than all of it not well. Should I go on? Don't complain or go on? Okay, I'm going on. Okay, so now we go inside of main. Now we want to, of course, keep the A part the same, right? This part's the same, but we want to change this to be done on the GPU. So the first thing we need to do is we need to allocate data on the GPU. So we allocate these device pointers, right? So we use our brand new function that does GPU alloc, which we defined upstairs. And so now the function is returning to us device pointers. Again, so these are pointers now that are only valid on GPU memory. There are addresses on GPU. And at the end, we need to free them. So I will do this here before we come out of this B area, okay? So we allocated these 2 device pointers, but they don't really contain any data, right? For that, we need to do the Cuda mem copies. So this will copy X1 and Y1 into the memory that we stored at we allocated at DX and the memory that we allocated at DY. And let's just check the direction is correct because it is host to device. Okay, we do that there. Good. Now there's one more thing because, okay, so I'll just say this first. And we want to also call the kernel. We still have here the old function, right? CPU function. So now we will give it, we will of course name it what we name the GPU function. So GPU adds P. But of course, now we need to pass not these X1s and Y1s, which are pointers to CPU memory, but now we need to pass the device pointers. We need to pass the pointers which point to memory which is on the GPU. So these DXs and DY. And of course, DX already contains X1 because we copied it there. And DY should already contain the elements of Y1 because we copied it up here. Okay. And this was a question we had, of course, if this is going to be GPU kernel, then we need to specify the threads. For now, we will just use one thread, right? Just one, and we'll worry about changing this later. Okay. What else? All right, so this will do the operation that we want. So this will take the data that we copied to DY and add it to A times the data that we put at DX. So we'll do the operation. But now the resulting array, right, the Y which is on the left-hand side of our equation that we want to compute. So, right, so it will do this on the GPU, but then this guy here is still on GPU memory, right? Because it's all done down there. And so if we want to do the difference here and check, we need to bring back this array to the CPU. So what are we going to do? We're going to do another mem copy like this one, but the other way around, right? So bring the data back. So I just copied that from up there. But now I need to, first of all, reverse the order, because I said the mnemonic is to imagine that there's an equal sign between the first and the second argument, right? So we're doing take dy, put it in y1. But I also need to change here the order, change it device to host, so that the runtime knows that the runtime, this tells the runtime that this is a device pointer and this is a host pointer and not the other way. Where was I here? Yeah, okay. And just to not be confusing, we will, yeah, this is not, this is not a good print line anymore, because we're not using CPUs. So change this to just write GPUs and pad it a bit. Okay. Good, good. So it seems like we're all set. Huh? So we added the GPU kernel. Let's go through this again. So we added the GPU kernel here. It looks exactly like the CPU kernel. It's just that it doesn't use OpenMP because GPU doesn't understand, the NVCC will not understand the OpenMP inside the GPU kernel. We added the global. We're using one thread. We're looping over the whole thing. And now when we call the GPU AXP here, down here, we're passing device pointers. We're passing pointers to memory that was allocated on the GPU. Okay, so let's see how many compilation errors I get. Go back to my NVCC line. Where is it? There you go. Okay. Oh, here, okay, yes, I forgot to remove this extra argument. Okay. And now, okay, if you try to do this, shouldn't. Then, okay, what the error is, Cuda malloc return 35. Basically, there's no GPU to run on. And the first error that happens is when you go to the first Cuda function here, Cuda, yeah, here, where you do the GPU malloc, then this comes out in error because there's no GPU to allocate memory on, because I'm running this on the front end, right? I'm not running this on the GPU node. So here it won't work. Okay. And so now I have to go back to my srun command. Hopefully this now will run. Drum roll. Okay. And so now it run. So this looks good. This looks single precision difference. 10 to the minus 15 is okay. But there's something definitely wrong here, right? So I'm definitely not able to read and write 19 terabytes GPU memory. So what went wrong here? Okay, so what I did here, I mean, obviously if this is the first time you're doing this, then there's no way you would have known this. But this kernel, this call is asynchronous, right? What does that mean? Asynchronous, it means the CPU is telling the GPU to run this and returning immediately. right? So the CPU is not waiting for the GPU kernel to finish. And that means that this T0 that this stopwatch, which I wrapped it around, it's basically just counting the time it takes to issue the kernel call, not the time it takes to actually run the kernel, okay? So that's why we get, so that means that T0 is very small, so it's much smaller than it takes, and that means that we're getting a fake sustained bandwidth, right? Because this is the denominator of the bandwidth. Okay. So it's pretty easy.
Could you repeat it a bit, please? I didn't understand why it doesn't wait for the CPU, what you said.
This is just this is how the model, the programming model is. So when you call GPU AXP, then this function here returns as soon as it immediately. You can assume it basically returns immediately. It is not waiting for the GPU to finish before returning. It's just the way it works.
Okay.
Okay. If you want, though, here we want it to return to wait because we're timing it. And so we can use this function, Cuda device synchronize, which basically says, wait for all the kernels to complete before I come back from this function device synchronize, okay? So yeah, so this is now indeed we are timing the time it takes to do the GPU AX plus Y, because we will only measure the time as soon as the function returns. Okay, and maybe you're wondering then, okay, well, if that's the case, then why was this difference so small? Well, because this function here that, you know, that asks for the data from the GPU, right? This waits for all the kernels to finish before it copies the data back, okay? So here we had an implicit synchronization when we called this Cuda memcopy. So this waited. So that's why the result was good here. But our timing around the GPU AXP was wrong, okay? Okay, so if I compile again now again. And let me just fix this because this bothers me a bit. Okay, let's see. Okay, that looks better now. So we're getting the same, well, unsurprisingly, the CPU hasn't, the first part of the code hasn't changed. So this bit that did in the CPU is still about 100. And we're getting this abysmal performance from the GPU, which is 0.2 gigabytes per second, right? And we said the peak is about 900. So this is 1,000 times, more than 1,000 times slower than what we would expect. Right? Okay. But that's natural because we are only using one thread, right? So now let's start building this up, right? So it's good that we did it like this, and we confirm that we get the same results. So at least the GPU kernel is working. Now let's try to build it up a bit. So first of all, we will use more threads, and we will begin by just using one block and 512 threads. Okay, so here we do 1, and here we put 512. Now, this will use 512 threads, so fine. But what does that mean? That means that 512 threads will run this kernel, and this kernel is operating on the whole array, right? Of course, this is not what we want to do. We don't want 512 threads to do the same thing. We want each of the 512 threads to do a part of the array. Okay, so we need to break this n into 512 and have each thread do a part of the n. Okay. To do that, we need to know, we need some way to identify the different threads within the kernel. And we know how to do that because we have these constants which I talked to you about that give you the thread index and the number of threads per block. Okay, so this is what we're going to use now. So, well, let me just copy these two in there. Okay, so I'm just copying them so that I don't have to type out thread_idx.x and block_dim.x every time. But basically, thread_idx.x, yeah, okay, let me go back here and just say that, okay, so I'm using just, so here I'm putting these scalars, not this dim3 thing, right? So these are just scalars and I'm just using one block. So the whole kernel will only run on 512 threads within one block, right? So that's all I'm doing now, which means that the number of threads per block is 512. And the thread index will be some number between 0 and 511, okay? And so this variable here will copy into ithread, the number of the threads, so from 0 to 511, okay, depending on which thread is running this kernel. But nthr, n threads, for all of them will be 512, right? Because that's the number of threads per block that I chose in the kernel. Okay, so it's another way of passing that 512 into the kernel. Okay, so now I have some way of knowing which thread is running this kernel. And I want to use this to determine which part of this iteration the thread will do. So I have this on the slide. So I will compute this n over n threads. So this LT will be the number of elements that each thread needs to compute, right? LT, because I have n elements and I have n threads. So LT is how many elements of the n each thread will need to compute. And then I modify the for loop so that it's I thread times LT. I'll explain this. I'll write it down and then I'll explain it. Yeah. Okay, let me take a sip and then I'll explain this. Okay, so, well, rather than explaining it, let's see. So if the thread which has I thread 0, right, enters this kernel. So the thread with I thread 0 is pretty easy to see what will happen. So for the thread with I thread 0, then it will start from I equals 0 and stop at I equals LT, okay? So it will do the first LT elements. It will loop over the first LT elements of this array. Okay, that covers the thread with I thread equals 0. The other thread, the next thread, which is running in parallel to this thread, is the thread with I thread equals 1. So that thread will start from I equals LT. So it will start from the next element that I thread 0 finished and go up to 2 times LT, right? So it will do the next LT elements and so on for I thread equals 1, I thread equals 2, sorry, I could do 3, up to I thread equals 511. So each thread is taking LT consecutive elements and computing them with the first thread taking the first LT elements, the second thread taking the second, etc. Okay. So that's what's going on there. Okay, is it clear? Anybody want to ask something here? So this is not the only way to do it, but this is the way we're doing it now, just to maybe it's easier to understand this way. So we compile it and we run it. And what do we get? What do we get? Okay, so we get the same result as before, so that's good. So nothing changed, right? We're doing the same operations before. And we're getting a performance which is 20 times better than before. So we use 512 threads, but we're getting 20 times the performance. So it's better, but not as much better as we would have hoped, right? Okay, so what did we do wrong, or what did we not do well? Well, so this is again something, of course, that how would you know this? You wouldn't, but that's why we're doing these exercises to understand. So there is some feature of the GPU that you should keep in mind, and that is that it is more optimal if contiguous threads access contiguous memory locations. So what does that mean? Well, first let's explain what we did before. So you can imagine, so this is one of the two arrays. This is either X or Y, it doesn't matter, but it's laid out in memory like this. So the 0th element is, you can imagine it at the top, or maybe you want to imagine it horizontally, it doesn't matter. But the 0 elements is up there, then comes element 1, 2, up to whatever, element n. And in the first iteration, the thread with index 0 is reading the 0th element. In the second iteration, the same thread is reading element 1, and then in the third iteration, the same thread is 0, 2, up to, okay, here I have K, but really this should be LT to be consistent with before. It reads the kth elements. Okay, and then we go to the next thread. So thread with index 1 now is when, you know, the 0th one in the first iteration, when this guy is reading 0, this is reading element K, etc. Right? So the same thread is accessing continuous elements of the array. This is very common on what you do when you do Pragma or MP parallel 4. This is how the threads distribute the work. So this, if you're used to programming CPUs or used to programming with MPI, this is how you think probably. But on GPUs, this results in so-called bank conflicts. So this is detail that I won't go into too much, but the memory is banked, meaning that continuous memory elements are served by different banks, and different threads need to access from different banks. So in any way, just to say that this is suboptimal, but what you want to do is the transpose of this, right? So what is optimal is if different threads access contiguous memory elements. So you want thread 0 to access the 0th element in the first iteration. And then you want the second element of the array to be accessed by a different thread in the same iteration, etc. So you just want to take this and basically transpose the operation, right? So instead of having one thread do continuous, you want one thread to jump, right? This is, again, I'm just repeating myself, this is maybe a bit counterintuitive to how you were doing it so far in CPUs.
This is because of the GPU architecture.
Yes, this is because of the way the memory is. This is a way of how the hardware is set up to access memory on the GPU. Yes.
And also because the threads execute simultaneously. So you want the memory to be next to the to each element to be nearby in terms of memory. Not sure if I am telling it correctly.
Well, I don't know. Maybe. It depends on what you mean. But it depends on what you meant there. But it's basically that just the way that these the way at which these the layout of these banks, which are used in hardware to access the memory, the way that they serve the different threads is that each bank will serve a different thread. Each bank is continuous in the memory, and so it's more optimal if you have different threads accessing adjacent parts of the memory.
Yeah, thanks.
But sorry, might be more optimal to exploit a higher number of threads, but isn't that limited by the amount of shared memory over threads?
Yes, we haven't used shared memory.
The communication.
We haven't used shared memory. And actually, in this example, we won't use shared memory because there's nothing to share at this point, right? So each thread does not need to share any memory with another thread because all the operations are just of I in the same line, right? So there's no data that a thread needs that is read by another thread in this case.
Okay, but maybe in another case when we need to exchange data between threads,
yes,
shouldn't that slow down the performance if we use a high number of threads?
Yes, and we will see ways. That's the next example that we will see some way how to, Good, yeah. All right, so how do we do this? Well, let's just write this down. So this is now our new GPU kernel, which I claim does what I showed in the previous slide. And if it's not obvious, that's okay. Maybe it shouldn't be. So I'll paste it and go through it and explain what it does. Okay, so the same code here, ithread and nthread. So ithread is thread ID, nthread is the number of threads. And now we're starting, so all the threads will execute the same loop, which is I equals 0, I smaller than n, and then I increments by n thread now instead of 1, right? But now thread 0 will do iteration 0, and then its next iteration will be when I is n thread. So thread 0 will do operation 0. Sorry, I should say not operation 0, but thread 0 will do line 0, and then it'll do line n thread, and then it'll do line 2 thread, and then it'll die 3 times n thread, right? Because it's incrementing this I by n thread. Whereas now if we go to look at what ithread 1 will do, ithread 1 will do line 1, then it'll do line 1 plus n thread, then it'll do 1 plus 2 n thread, etc. up to the end. And then the thread with ithread 2, so forth, will do the line 1 with the line 2, then it'll do 2 plus n thread, 2 plus 2 n thread, 2 plus 3 times n thread, etc. Right? So it is trying to implement this approach. Let's save it there, and then I'm going to compile it again, and then let's run it and see what we get. Okay. So now I got something which is 3 times better. So about 12 gigabytes per second. And now this is basically it. I just need to throw more threads at the problem, right? So this approach is, well, again, I'm telling you this is not that you can, that for this very simple kernel, this sort of reaches the limit of the optimization we can do. And now just by throwing more threads at it, we should get close to the 900 gigabytes per second, which I said is the peak performance of this GPU.
Will there be any difference if you calculate only once the index and store it to a local variable? I mean, the I plus I thread. Will this make a significant difference?
How many times am I computing it?
3.
You mean here?
Yeah.
I think it will optimize that out. Let's see. Okay, that's a reasonable question. That's how you should think. Very good. That is exactly how you should think. But I'm pretty sure this is already optimized by the compiler. But in any case, let's try.
So most probably this will work on Python, but not on but not in C. Yeah.
So that looks the same to me.
Yeah.
Yeah, because it's probably already looking. The compiler can already probably see that and make a local variable.
Yeah. Okay. Thanks.
Maybe if the calculation was more complex, would make a change.
Yeah, maybe. Yeah. No, but that's a good example of how you should think. Yes, very good. Okay, so as I said, now we just try to throw as many threads as we can at this. So let's use as many threads as there are elements of this array, right? So let's use n threads, right? N is the size of the array. So let's just use 1 thread for each element. So that means, so I said that there is a limit here in the number of threads per block that you can use. This is 1024 for this model. But you can effectively think, you can effectively consider that there are no limits in the number of blocks, right? So the number of blocks can be 2 to the 30. You'll never run out of blocks. Don't worry about the blocks. Okay? You'll never run out of blocks. 2 to the 31 minus 1, you won't run out of them. So that means that I can use the maximum number of threads here. And then if I want to have as many threads as I do elements of the array, then of course, then here I have to do 1024. And just to make sure I don't make mistakes later when I change the number of threads, I'll just use a variable, not for any speed. This is not making it faster or anything. It's just that I want to have 1 variable to change here and then have it be correct. So so I'm using 1024 threads and how many blocks I need to fill the array. And so now I need to go up here. So now I'm using more than 1 blocks. And so that means that I also need to know in which block this thread is. Right? Like this. Okay. And so now iThread is not anymore the is not unique anymore. ithread is just the index of the thread within the block. What I want is the index of the thread over the whole grid. And so that means I need to do this well-known index calculation, which computes the global index now, right? So it's the index of the thread within the block plus the index of the block within the grid times the number of threads per block. And now IDX is unique to all the threads across the whole grid of blocks. And there's no loop anymore, right? Because each thread will just do one element. There is no need for a loop. So let's get rid of that. Let's get rid of that and just replace that with IDX. Okay. So thread 0 will just do line 0. Thread 1 will do line 1. Thread 2 will do line 2. Yada, yada, up to thread n-1, which is the last thread, which will do line n-1. No loop necessary. We just have as many kernels as we have elements. So I've hidden the loop inside the fact that I can have as many threads as I want, right? So I've sort of obscured the loop into that. Okay. Let's see now. I got 719. Today I'm getting 720. And okay, not clear why, but sometimes the maximum number of threads is not the optimal number of threads. So you can play with this a bit, maybe use 128. And notice now, if I change this to 128, it'll, this calculation I'm doing here will just increase the blocks so that again, I have as many blocks as I need so that I have one thread per element, right? So I don't have to change anything else, just that n thread to 128. At least that's how I set it up. And so if I run again, I should get the same difference here. So it should be still correct. And yeah, okay, slightly better. I don't know, let's try one more. Let's try 56.
Can you also try to increase the size of the array?
Yeah, I can. I don't want it to get too big because, well, actually this won't get too big. Okay, so that's closer. Let's try 256.
So
Okay.
it does basically the same time. Or no, I'm wrong.
No, it takes longer, but the
Yeah. Oh.
okay, so you can probably get, by playing with it a bit, you can probably get up to 800 gigabytes per second, which compare it to the 900 gigabytes, which is the peak, is relatively close to the peak. Again, this is a very simple kernel. You shouldn't expect to get so close to the peak, usually as much, but for these simple kernels, you can really see the hardware limitations of the GPU. Okay, so some caveats of what I mean, some things to warn you. I mean, I'm sure you'll ask me about this when you think about it a bit. So I'm using powers of 2 everywhere here just to make sure that the number of threads divides the number of elements exactly, and then the number of blocks divides, so that the number of blocks is a nice integer number. Of course, if you want to make this general, then you have to take care of that somehow, right? You need to be careful so that, for example, the last block here does not go over the end of the array. You need to be careful about that stuff, but there's all sorts of little if statements and stuff you can do to take care of that. So, but yeah, I just want to warn you that I'm not checking for these because I'm just making sure that all my arrays are the nice round powers of 2 and also that the number of threads is about to, etc. But there's no reason, of course, for it to be like this. Okay, so this concludes our warm-up with Steyo. Is it 15 minutes to the break now? Okay, so before I move on, any question you might have? Yeah. Yeah. So, yeah, thanks for that, because I sort of glossed over it. Okay, so this is the loop, right?
Sir, could you please repeat the question because we didn't.
Yeah. So the question was that whether I could explain how I calculate the gigaflops and the gigabytes that we're writing there at the end of the program. So what I'm just to be clear, what I'm writing is the sustained gigaflops and gigabytes per second. So this is just a statement about not necessarily oh, well, let me say it like this. So if you just look at this kernel, okay, so let's do the gigaflops. Let's do the flops first, right? So every iteration here needs 2 floating point operations to complete, right? Because you need to multiply a with x and then add y. So the number of single precision floating point operations per iteration here is 2. Incrementing this is, of course, an operation. Integrate, so there's no floating point operations there. So yeah, so there's 2 flops per iteration there. So how do I compute it? Well, I know how long it takes to do n iterations because I'm timing it. And I know that every iteration is 2, so I just do the simple division, right? So it's 2 times n over the time, 2 floating point operations. Okay. The gigabytes per second now is a bit of a fuzzier statement, because what I'm assuming is, well, it has more assumptions. So I'm assuming that y is in memory, it's not in cache, and x is in memory, so it's not in cache. So this is what I'm assuming. And that in order to do this operation, I need to take all elements of y from memory, take all elements of x from memory, and then write back again y to memory. So that's the assumption. So that means that for this kernel to complete, I need to read or write 3 times n floating point numbers from or to memory. That's the, right? And for the GPU, that's a reasonable statement because it basically has no cache, right? The GPU has, the amount of cache is so small that you can assume it has no cache. And so if you want to complete this operation, you need to indeed read for each element 2 and then write 1 to memory if you want to complete this. And so that's why, yeah, I have this calculation here. So n flop 2, NOO is 3 times size of float. And then what I'm doing here when I'm writing it is n flop times n over, this just turns it into giga, right? Gigaflops rather than just flops. And then
Ναι, να σου πω, άκιμος, ναι.
Yeah.
Κοίτα, μου χάλασε ο φορτιστής του λάπτοπ μου. Έχω έναν άλλον που είναι πολύ πιο αργός, αλλά θα
Yeah, close your
δεν ξέρω,
microphone.
νομίζω, δεν ξέρω. Μου χάλασε, αλλά είμαι μέσα στην εγγύηση, οπότε δεν με πειράζει.
Okay. Does that, yeah? Does that cover you? Yeah. Good questions. More, please.
Um,
Yeah, Nicola.
Kind of forget, but give me a few seconds.
Okay. Okay, so what we learned then, at least maybe I can say this. So we learned a bit here, some of the take-home messages. Okay, GPU kernels return immediately. That might be useful if you want to do something on the GPU and then continue doing something on the CPU and then copy the data back. So GPU kernels run asynchronously. So that's one thing we learned. In order to exploit the GPU optimally, you need to use as many threads as you can, right? And then the system just deals with distributing. I mean, yeah, okay, that's why it's good to summarize. So here we're using, so the last time I run this, I used 256 times 1024 times 1000. So I used 256 million elements I had of X and Y. And of course, the GPU does not have 256 million cores to run, right? But what I do is I define these blocks and these threads per block, and then the GPU runtime just decides how to run these. So these, you know, this operation here that I'm doing, where I'm just computing the index, and then, you know, I have all the threads. I have one thread per element. Of course, these 256 million threads are not running all in parallel. There's not enough hardware on the GPU to run everything in parallel. But the runtime of the GPU is, you know, optimized in hardware to decide how to distribute these different blocks. So some run first, some run second, etc. But in the end, it looks as though the way I program it is as if these all run in parallel, right? Right. So it's an abstraction of parallelism, which is a bit higher than what you might be used to with pthreads or OpenMP, etc.
This is very nice. That was actually my question. And if, for example, I want to buy a very good GPU, then I will prefer to have it to have more threads, right? So because the 1024 threads are executed in parallel, or I'm thinking in the wrong way.
Those 1024 are running in parallel, but also several blocks are also running in parallel.
Yeah.
And how many blocks are actually running in parallel is, okay, depends on the hardware. I mean, there's many things to consider. It's not just the number of threads, it also depends maybe on how fast the threads are.
Yeah, if everything else is the same between two GPUs, for example.
Yeah.
Okay.
Then you're saying the number of concurrent threads is the determining factor.
Yeah.
Yeah.
Okay.
Sorry.
Thanks.
Hello.
Yeah.
So my question is, what happens if the arrays are not a multitude of a power of 2, and like you have something in between? Is it better, for example, to leave like some array element to run it full, and the last iteration has some empty threads, or does it?
Yeah. So if you would just check here if this is the last block. So you would check if block IDX is at the end, and just have the threads that participate, that, you know, just have enough threads to end the calculation. So if I go back to this picture, okay, let's go back here. Okay, so of course we're just one-dimensional in our case, right? So you're saying, so the number of the array starts from here and then somewhere in the middle here, right? Okay, so So what you would do is check if you're this block, and if you are this block, then have an if statement to only have these guys do something and these guys not do anything.
So is there a point in distributing, let's say, the inactive threads in different blocks, or should it be like you have only one block which just you take the loss, let's say?
Say that again, sorry.
For example, if you're using 4 blocks, instead of having, let's say, three blocks fully with full threads and 1 block with, let's say, 1/3, you have all 4 of them with a percentage of threads active.
I don't think I can give a recipe for that. I guess it just depends, and you should just try and see if you have, I mean, if you have hundreds of blocks, right? Then probably it's better to fill the blocks and let the 100th one just use the, a subset of the threads. That's the first thing I would try, but it depends on your problem whether it's more optimal to have a different number of threads per block, and then a number of blocks that will fill your problem exactly. I don't know. I guess it depends on the problem. It's for technical reasons, it's usually best to have at least 32 threads per block and multiples of 32. But not so that seems to be a sweet spot just because of the way of the execution unit of the GPU. That the instructions are issued per 32 threads, right? So each 32 threads, they form this so-called warp. We might say a few things later about it, but but breaking up the warp into less than 32 threads per block might be suboptimal. That's the only general rule maybe that you might need to keep in mind. But other than that, it's mostly testing. A lot of complicated GPU application programs have their own tuning procedure in which there is either a benchmark you can run before you start production, or a or a program or a routine that is run upon first run, where they scan the number of blocks and the number of threads per block for given kernels, and then store the optimal. So a lot of even application codes will just scan for this, because it's difficult to predict unless you actually run on the hardware for a given problem size.
Okay, thank you.
I have a quick question, if I may.
Yeah, Petra, Giannis is asking. Sorry, I'll repeat Giannis' question and then.
Oh, I think it wasn't heard. I said thank you.
Another Giannis.
Oh, sorry.
Too many of us.
Okay, just a question about the this specific problem. We have an array that is shared among the threads. Okay, because they write to the same array. We have different threads, so there is some sort of shared memory, I think.
Not the way we mean shared memory. Not the way we mean it in this.
Is there a copy in each thread of the array, or?
So the question was a question about shared memory. So if we have in mind this picture here, right? So if you can imagine that the arrays X and Y are sitting in global memory horizontally like this, right? Okay, so what we call in this CUDA terminology as shared memory is some memory that is shared within the block, okay? And we don't have this in this problem. We don't have this kind of shared memory, right? Why? Because each thread will just read one element of X and one element of Y and put it back in Y, right? In the same element Y. So there is no crosstalk between the threads, right?
Also, they read from the global memory.
They read from the global memory. So global memory is also shared. I mean, you're right. I mean, but in this, but in this terminology, shared memory, we mean this, which is the common memory between the different threads. Okay, it's just the way, it's just the naming convention that is used. So yeah, I mean, yeah, I see the confusion, but we didn't use any of this kind of memory.
So they read from the global memory, the array.
Yeah.
Thanks.
Okay, we break for lunch. Oh, no, no, sorry, Petra. Oh my God, forgot.
Yeah, probably it's similar. So in this function, you have y and like in the same index, and you are summing it. Yeah, if you go back to the function.
To the last one? Oops.
Yeah, the elegant one when you skip the for loop. Yes. So basically, you are summing up the information that it's in the same index in y. But let's imagine that you want to sum the one that was in the previous one. So idx minus 1. Let's say you want to access the data in the index that was before. So I suppose you would need to go back to the for loop. But is there any communication in between the, let's say, the memory that it's in the IDX, the previous one, because now all of it is in a different thread? Okay. I'm not sure you understand my question.
No, that's really good. So what if I had, you're saying, what if I had a different operation, right? So this would be different, where you would need to do x of IDX minus of IDX minus 1, something like this.
Exactly, yes.
Okay, yeah, so that is somewhere where you would need to either have this thread access also IDX minus 1, right? So that would mean more than one threads need to access more than this, the same location in memory, which is fine. You can do that. So you can just write IDX minus 1 here. Or we should use shared memory, which we will learn about in the next example. Okay, so yeah. Is that a satisfactory answer? So I mean, there's no problem to write here IDX minus 1. Nothing prevents you from doing that. It just means that the thread with index IDX will read the element of X IDX, but will also read the previous element. That's fine. It's not optimal, but you can do it. You can write IDX minus 1.
Okay, thank you.
Okay, but there is also a way to have it so that all the threads read their own elements, and then they share it with their neighbor so that the neighbor does not need to read it again. So there's also a way to do that, and that is with shared memory. Okay, which we will cover in the next exercise. Okay. More questions. These are good questions. And maybe you think of some over lunch. So we come back at 2 in 1 hour. Okay. Good. Thank you all. We'll be back in an hour.